Hello everybody, my name is Nikita. I'm a PhD student at Cornell University, and in this talk I'll be presenting our work on Dagger, efficient and fast RPCs in cloud microservices with near-memory reconfigurable NICs. This work has been done in collaboration with my colleagues from Cornell and under the guidance of Jiru Zhang and Christina Delimitro. We will start our discussion with the overview of the modern trends in cloud computing and the ways they change requirements to the cloud communication stacks. A traditional cloud application, or a monolith, represents the whole application logic as a single statically or dynamically linked binary. The applications might span across multiple machines, however they still remain coarse granular. This approach has multiple fundamental limitations, especially when it comes to development and releasing cycles. In order to address these limitations, modern applications are moving towards microservices that represent the application logic as many independent small applications communicating with each other over the network. Another similar trend here is shift towards serverless, where in addition to fine application granularity, we also have fine lifetime granularity. Another trend in cloud computing today is interactivity. Cloud applications frequently interact with a large set of users, which introduces strict performance requirements as their service level objective function, such as low tail latency under high load and performance predictability. The interactive nature of microservices already creates relatively high requirements to cloud communication stacks, and making the applications fine granular further puts the bar even higher. The inter-microservice delays, which are typically in the order of hundreds of microseconds, eventually propagate through the deep microservice call graphs and result in relatively large delays as observed by the users. Moreover, networking queuing that might happen in between microservices also gets accumulated and causes cascading quality of service violations, which might eventually destroy the user experience. In this work, we are focusing on improving communication stacks in microservices. So let's see what are the unique requirements and challenges that microservices introduce in cloud communication stacks. Microservices typically communicate over remote procedure calls, or RPCs. In order to characterize the request latency breakdown across communication stacks, we run the microservice benchmark suite DevStar bench that consists of 36 microservices on 16 different machines. We further measure how much time each request spends in different parts of the communication stacks and show the results for 6 services from the benchmark on in this figure. We record both the median and tail latency for 2 types of workloads, 100 queries per second and 800 queries per second. The green part of the bars correspond to the time requests spent in the applications, the yellow in the RPC layer, the red in the networking stack that includes both the TCP/IP processing and input-output. This figure basically shows that the requests spend a lot of time in communication stacks, and for some of the services, this time even exceeds the time requests spent in applications themselves. Second, RPC requests in microservices are small and vary by tiers. This figure shows that for the social network and media service benchmarks, more than 90% of messages are smaller than 512 bytes. Moreover, the sizes of RPC requests and responses vary by tiers. For some of them, they are small, but for some of them, such as S4 and S6 services, they are relatively large. These results show that per-request communication overheads in microservices are large due to the fine granular nature of requests. And we cannot just tune communication stacks for small messages only, so we need an adaptive stack that efficiently supports both the large and small requests. Finally, RPC stacks usually run on the same CPUs as highly concurrent applications. Applications in microservices today might run hundreds of threads and hundreds of connections at the same time. So this already introduces high pressure on the CPU and its memory subsystem coming from the applications. Handling intense traffic of small messages on the same set of CPU cores and the same processors makes this pressure even more. This figure shows how the end-to-end application latency might go up when running networking processing and application processing on the same set of cores. In order to address the aforementioned challenges with networking stacks in microservices, we propose Dagger, a hardware-software co-designed and host RPC stacks, which is built with the specific requirements and network footprints of microservices in mind. Dagger is based on 3 design principles. The first principle is hardware offload. Let me briefly overview the existing techniques to improve efficiency of cloud networking. One set of techniques is based on kernel bypass systems, where the packets are being immediately delivered from the networking hardware to the application. This allows to remove per packet kernel overheads from the critical path of packet processing and tightly couple networking stacks with applications. However, here we still run everything in software, which consumes CPU cycles and interferes with the application logic. Another set of proposals offloads network processing to specialized hardware adapters by leveraging remote direct memory access systems. This allows to improve the efficiency and performance of cloud networking stacks. However, RDMA only provides low-level abstractions, and the RPC parts should still be implemented on top of it and run in software. Also, RDMA systems require specialized adapters. The Dagger's principle along this dimension is full hardware offload. We design a hardware NIC for end-host communication stacks that offloads the whole stack from the L1 physical layer and all the way up to the RPC layer. This way, we completely free CPU from doing any work related to data exchange. This principle is shown in this figure here. The Dagger NIC implements the communication stack from L1 to the RPC layer and only communicates ready-to-use objects with the applications, both on the client and server side. And the only operations that clients and servers need to do is just reading and writing RPC objects into the dedicated pre-allocated memory buffers shared with the NIC. Our second design principle is reconfigurability. Existing software-based RPC stacks, such as Thrift, gRPC, and so on, are modular and configurable. They provide a flexible choice of networking protocols, load balancers, threading models, the ways how data are represented and manipulated. And if we want for our hardware-based RPC stacks to be equivalently flexible and therefore practical, they should also be configurable. For this reason, Dagger is based on an FPGA. FPGAs have already been identified as a good physical medium for networking devices and to accelerate network processing. They can handle large streams of networking data at the line rate for the speeds of 100 gigabits per second and even higher. So with FPGAs, hardware offloaded RPC stacks can actually be fully customizable and practical. Dagger allows the flexible choice of the transport layer and is currently based on the UDP. However, it can also support TCP/IP for FPGAs, specifically optimized transport layers for particular workloads such as MTCP and HOMA, and also reconfigurable transport layers like Tonic. Dagger also comes with configurable load balancer and flow controller. Load balancers are very important for end-host RPC stacks as they allow to define the exact way how RPC requests are delivered to different threads on the server side. Currently, we support the static, round-robin, and random schemes, as well as application-specific load balancers, such as key-value-based for partition key-value store systems. Dagger also comes with a reconfigurable Host-NIC interface that is based on the commodity PCIe Express scheme and our proposed coherency-based approach that we will discuss later in this talk. Finally, Dagger defines configurable across 3 dimensions threading model. Let's talk about this a little bit more. Across the first dimension, the Dagger's threading model allows to define how connections, application threads, networking queues, and NIC flows are mapped to each other, and also specify the number of NIC flows and queues. Here we have 3 basic schemes. The first one is called single queue model, where the NIC runs a single flow corresponding to a single queue being shared between all CPU threads and connections. Previous studies have shown that this model performs best in terms of the load balancing. However, it might suffer when running in highly concurrent environments due to the needs of exclusive locking of the queue between the threads. This issue is addressed in the shared queue model, where NICs run multiple flows, each flow having a separate queue that corresponds to a separate CPU thread. This model performs better in highly concurrent environments, however, it might suffer from load imbalance. The final model that we support is called connection basis model, where we provision networking flows and queues per connection basis, such that each connection gets a separate queue and separate flow on the NIC. This model works best in highly concurrent environments, however, it still suffers from load imbalancing, and it doesn't necessarily scales well, especially with the large number of connections. So basically, the exact threading model can be selected based on the application requirements, and therefore we think having this option reconfigurable in hardware is a good design decision. Along the second dimension, our threading model defines how RPCs are handled by the server. Here we can process RPCs in dispatch threads, which is good for short RPCs with low latency requirements, or in worker threads, which is good for long-running RPCs. Finally, the Dagger's threading model defines two types of connections, blocking and non-blocking. The third and final design principle of Dagger is tight coupling. Dagger is based on a cache-coherent FPGA tightly coupled with the host CPU. This design principle is inspired by the scale-out NUMA work and a series of RDMA studies showing that PCI Express introduces non-negligible overheads, especially when it comes to delivering small messages in high-performance request-response protocols. Unfortunately, existing smart NICs, including FPGA-based smart NICs that could have been potentially used as the physical medium for Dagger, are all based on PCI Express, and they all suffer from these overheads. So what's the problem with PCI Express and high performance and host-X? The root cause of performance issue here is the doorbell scheme. This is the way how hosts exchange data with networking interfaces. When the processor wants to send a piece of data over the network, it first issues the ring the doorbell transaction, notifying the NIC about the new data available in its transmission buffers. And then the NIC runs multiple DMA transactions in order to read the data descriptors and the packets itself. So multiple PCI Express round trips are required to send data. And every transaction starts with expensive and CPU inefficient ring the doorbell messages based on memory mapped IOs. There have been multiple optimizations proposed along this line, including combining descriptors and packets together into single DMAs, or writing packets directly with the MMIOS transaction, therefore avoiding DMAs, or batching transactions together and notifying the NIC about the whole bunch of requests. However, neither of them actually allows to eliminate the expensive ring the doorbell message, which is the bottleneck here. So what is a cache-coherent FPGA? A cache-coherent FPGA is an FPGA that acts as a NUMA node. Consider the basic multi-socket setup where multiple CPU cores are connected to each other over a NUMA bus, and replace the second processor with an FPGA. This approach has multiple advantages when it comes to delivering data from CPU to FPGA. First, there is no needs in DMAs in order to send data between NUMA nodes. There is no needs in explicit memory mapped IO request either. This scheme minimizes software overheads related to data transfer because the data exchange is being handled entirely by the hardware cache coherency state machine. Finally, NUMA interconnects have physically lower latency. A typical NUMA bus has the one-way latency of 250 nanoseconds versus 450 nanoseconds for PCI Express. Now, let's see how Dagger is designed and implemented. Dagger is based on the Intel Broadwell Xeon FPGA hybrid architecture that integrates a server-class Xeon processor with a large FPGA in the same packet. The processor and the FPGAs here are connected to each other over both PCI Express and UPIe NUMA interconnect. Other hardware platforms, such as the ones listed here, can also be used as an alternative physical medium for Dagger. This figure shows the top-level overview of our RPC stack. The bar on top shows how the Dagger RPC stack is mapped to the Thrift RPC stack. The software part of Dagger runs on the host CPU and implements RPC stubs that expose the RPC API to applications and read and write RPC objects to the shared with the FPGA memory buffers. The FPGA runs the hardware part of the stack. That consists of the RPC pipeline, with the CPU NIC interface as the first component. The CPU NIC interface fetches objects from the processor and sends them to the RPC layer that does the connection management and implements the RPC protocol, and further sends messages to the transport layer, which directs them to the outside world over the Avalon network streaming interface and the Intel physical FPGA networking infrastructure. The Dagger NIC also has a couple of additional components, such as the reconfiguration unit to flexibly control the RPC pipeline and the packet monitor for debugging purposes. The CPU to NIC interface and transports here are designed to be configurable such that different options can be selected based on the requirements and traffic patterns of the target applications. Now let's move to evaluation. We first compare different host NIC interfaces under the single core transfer of 64-byte requests. As I mentioned earlier, Dagger runs multiple host NIC interfaces. One of them is based on memory mapped IOs. It's a well-known optimization for PCI Express transfer where all the requests are being sent only using MMIOs, therefore avoiding DMAs. This is shown with the green color on this chart. Another interface is based on doorbells and doorbell batching, which combine multiple requests to batches and sends them with a single doorbell. And finally, the red bars here show our NUMA-based transfer. So the figure here demonstrates that NUMA-based interfaces deliver up to 1.1 to 1.8x higher throughput with up to 2.5 times lower latency. In the next experiment, we evaluate the scalability of Dagger with the number of CPU cores when transferring 64-byte requests. The figure here shows that the throughput of our system scales linearly up to 4 cores and reaches 40 million requests per second or 80 million requests per second, given that we are running both client and server on the same node. The figure also shows that there is some certain scalability limitation here. Our experiments with socket-to-socket NUMA communication show that the actual NUMA bus is pretty fast, and in theory it can provide an end-to-end system throughput of up to hundreds of millions requests per second. However, in our current prototype, the UPIe bus is implemented using soft logic on the FPGA. And soft logic on the FPGA is in the order of magnitude slower than ASICs. Therefore, the current implementation of the coherency interconnect is not optimal here, and this is the reason of this performance scalability limitation. Fortunately, upcoming generation of cache coherent FPGAs can address this issue because they all implement cache coherent interconnects in hardware using hardcore IP cores. In the next experiment, we run end-to-end key-value store applications such as MICA and memcached on top of Dagger and show its performance of transferring small and tiny messages. Since Dagger implements the high-level RPC abstraction, it's pretty easy to port third-party applications to it. In particular, it took 50 lines of code for us to run MICA and 200 lines of code to run the memcached server on top of Dagger. Our system brings the remote key-value store access latency down to the microsecond level, which is roughly 4 times slower than the numbers reported in the original MICA work when running the key-value store system over the highly optimized DPDK-based kernel bypass system. Finally, we show that Dagger supports multi-tenancy and it can be used to implement chains of microservices. For this, we implement a synthetic flight registration application that consists of 8 tiers and connect all these tiers to each other over the Dagger RPC. We instantiated a separate version of Dagger per microservice, and we also configure the load balancer threading models of those Dagger NICs differently depending on the requirements of different services. This figure shows the characterization of our system. So in conclusion, I would like to emphasize again that Dagger is a hardware-software co-designed reconfigurable cloud RPC stack. It's based on the end-to-end hardware offload and tight coupling with the CPU and application, which allows us to get microsecond scale tail latency, small per packet overheads for small messages, and low CPU pressure, both on the cores and memory. Finally, It's based on an FPGA and is therefore reconfigurable and practical, and it can support diverse needs of fine granular cloud applications. This is all for my presentation today. Thank you for your attention. Please watch our live talk on April 19 at 7:40 a.m. Pacific Standard Time, followed by the Q&A session.